Alright, our key conquest continues with problem number 3 from the take-home exam. As you may recall, problem number 3 was a multiple part question, the first part of which was to show how in this particular reaction the reaction takes place. In other words, draw the mechanism. So what we had was TBAF, tetra N-butyl ammonium fluoride, and this molecule, this unsaturated 3-carbon aldehyde, reacting with the dye-protected silyl enol ether here to give what for all intents and purposes sure looks like an aldol product. And that's because it is an aldol product. So how does this work? Well, you guys all know that the fluoride anion is a very good reagent for cleaving silyl oxygen bonds. So the very first thing that happens here is, and I'm just going to abbreviate this OTMS for trimethylsilyl, that enol ether gets deprotected, and what you can see from that is that you have an enolate. So if I just draw that resonance contributor, I can see that anion is just rip-roaring and ready to go, and it can react with my unsaturated alkene. Now here's a question that you should have had, and that's why I was trying to hedge off at the pass. I would have predicted it would have reacted here. Clearly there are other things going on that I didn't tell you about. The researchers added cerium, I think it was cerium anions too. No, I can't remember what they added. But basically, they controlled the conditions such that it went 1,2 instead of 1,4, and that's what gave you your aldol product. I'm not even going to show the rest of the mechanism. The cleavage of the TMS ether on the right-hand alcohol is just the same as the cleavage of the TMS ether on the left-hand molecule. So that was the very first part of the problem. That was the formation of beta from alpha. Next, we have to provide the reagents and conditions for A and B. So basically, A was taking this aldol product and, interesting. Chapter 21? Nope, Chapter 20 chemistry. In other words, I am taking an alcohol and making an ester. So what that tells you is what you need to add is some kind of carboxylic acid derivative. And yeah, you could add acetic acid and an acid catalyst. That's really problematic though, because you have a very vulnerable hydroxyl group here. So that's not the best way. It would be a lot better if we had something much more reactive than the acid. So really the way to go here would be to add the acid chloride, and a base, a good base would be something like pyridine. And that would very happily acylate your alcohol. Now, question number 2 you should be wondering about. You have 2 alcohols here. How come I am able to selectively add to that one? Well, this is an example where sterics is your friend. This being a tertiary alcohol down here, it's a lot less reactive. It's going to be more crowded, and it is going to be easy. Well, easy. It's definitely going to be feasible to put the acetyl group on that one hydroxyl group. No problem. So once you've done that, what do you got? Well, you have a great leaving group. And so you're all set up for an E1CB reaction. So I can take a base, any base. Tert butoxide be fine. Ethoxide be fine. Even an amine would be fine. And all I have to do is do that to ensure that I get mostly elimination. I should also add heat, because heat favors elimination. So those are the reagents A and B. Now the rest of the problem has to deal with an alternate route to their desired product. And that alternate route started out with this guy. And so they wanted to take this and convert it to this. And that really means I have to think about how am I going to make that into a nucleophile, something electron rich. So that really means either generating the enolate or, under acidic conditions, the enol. And seriously, acidic conditions again would not be a good choice because of this guy. So the best bet here would really be to figure out how to do this reaction under basic conditions, and that's pretty straightforward. You just need your bromine electrophile and something to generate the enolate. So this is back, this is, I don't know, 528, page 528 or so, whatever chapter that's in. It's kind of older stuff. I think it's actually 2301. But there you can put your bromine on there using those reagents. That's J. That then reacts with this phosphine, which is, of course, a nucleophile. And now I have umplunged that carbon so that it's now an electrophile. So my product K is this guy. I'll put an R there because I'm running out of room. Okay, so this is a phosphonium salt because the counter ion is the Br minus. This is not what goes on to make the alkene. You have to convert this to the ylide. So the product K is this guy. This is somehow or other converted to this guy. So clearly I would appear to be adding this. And that ought to be able to be done by a Wittig with this. But before I can get the Wittig to work, I have to convert my phosphonium salt into the ylide. So that means I have to deprotonate one of those two hydrogens. Remove one of those two hydrogens, that makes the ylide. That makes this guy. And it's this guy that reacts with the aldehyde to make that diene. So that is problem number 3, and we'll close off this recording, keep it short and sweet, and have another little mini lecture for the next problem.